Sagurika, you may have seen that over the modules 1, 2, 3, 4, Bikesh was continuously coming back to CRD, CRD, CRD. It seems he was not willing to go beyond CRD. Now the time has come that we are really going beyond CRD. In this module 5, I will take up RBD and LSD, but we will be taking a mature point of view. We will see what RBD and LSD are all about. You already know many basics about these two designs as you have studied in your undergraduate course, but still we will look at these two things from a mature point of view. Okay? So let's start with RBD and LSD in this chapter. Let's quickly go through the RBDs and LSDs as we have studied in our undergraduate course. As a matter of fact, after I myself studied these topics in Statistics Honours course for the first time, I felt that the course description only covered the methodological aspects of data analysis underlying such designs. The subject matter is highly interesting, logical and sufficiently technical and advanced, but that appreciation to me come much later. As it happens, at this stage, we only carry out a routine ANOVA data analysis. You have to wait till we discuss about general block designs and row column designs in subsequent lectures to really appreciate the deep insightful thinking that is going on in the data analysis. And you recall what you mentioned about RBDs. You talked randomized block design, one single blocking factor, one-way elimination of heterogeneity design, two-way ANOVA model. These are all synonyms. We start with the basic premise that the experimental units to start with are heterogeneous and that there is one single blocking factor which divides the experimental units into homogeneous sets, technically called blocks, right?
Yes.
And then there is something more to it. RBD tacitly assumes that each block contains as many experimental units as there are treatments whose effects are to be compared. This suggests the total number of experimental units to be n equal to b times v, where b is the number of blocks and v is the number of treatments. You have so many treatments to be compared, there are so many blocks available. In each block, we should have as many experimental units as there are treatments. That is the peculiarity of RBD. The experimental units in each block receive every treatment exactly once, and the treatments are allocated in a random order in every block. That is the peculiarity of the randomized block design. The CRD model is now generalized to an RBD model where we should bring the block effect into the picture. So now YIJ refers to the output arising out of the block I and treatment J combination. So the model is YIJ equal to mu plus beta I plus tau j plus EIJ. So let me go back to the model again. So IIJ is the output received by a combination of the ith block and jth treatment. It's a single combination. Therefore, we get only one for this combination. Mu is the general effect. Beta I is the excess effect of the block I in addition to mu. Tau j is the excess effect of the block treatment j in addition to mu, and EIJ is the usual error component.
Yes, sir. I know the obvious interpretation of the notations or symbols involved in one. I also know the formation, actually, I mean the structure of the ANOVA model, which is actually we have three sources of variation. One is for block, another is for the treatments, and the last one is for the errors. The degrees of freedom corresponding to the blocks are b minus 1. SS, that is sum of squares for the blocks, is equal to summation sum over I bi square by v minus the correction factor, that is CF. And the MS of block is equal to SS block divided by b minus 1. So the F ratio is F is equal to MS block by MSE. Again, for the treatments, the degrees of freedom will be v minus 1. The sum of squares for the treatment is equal to sum over j treatment of treatment J square by B minus the correction factor, and the MS treatment will be like this. So the F ratio is equal to MS treatment by MSE. And finally, the error degrees of freedom will be N minus B minus V plus 1. The sum of squares of error is equal to SST minus SSB minus SS treatment. And finally, the MSE is equal to SSB by N minus B minus V plus 1. That is the degrees of freedom. So here is the total degrees of freedom, that is N minus 1, and total sum of squares, which is equal to sum over ij, yij square minus the correction factor.
So note that in this table, the mean square computation for the total does not make any sense. Mean square computation for the blocks, yes. For the treatments, yes. For the errors, yes. That is number one. Number two, this BITJ, they refer to the subtotals of outputs. YIJs are the outputs. BI refers to the sum total of all the Ys in the ith block, and TJ is the sum total of all Ys corresponding to the jth treatment.
Yes,
that is how BI and TJ, those are computed. And the error sum of squares comes from the subtraction because of the important result that the total sum of squares is nothing but sum of squares block plus sum of squares treatment plus sum of squares error. That is called the orthogonal splitting of total sum of squares.
Yes,
it is
sir.
because of that result that you get error by subtraction. So
Yes,
this
sir.
table, as you know, is very easy to compute the all the components
Values.
over
Yes,
here.
sir. Yes, sir. And as I have told, that CF is the correction factor, which is capital G square by N, and BI is equal to sum over J, Yij, and the treatment J, suffix J is equal to sum over I, Yij. And G is equal to sum over Ij, Yij. That is
That is double summation.
Double summation. That is the total
Okay.
sum. Now further, we have two valid F tests, one for each hypothesis concerning the equality of treatment effects and that of block effects.
You mean to say the first F ratio that refers to blocks,
Yes, sir.
and the second F ratio that refers to treatments.
Treatment. Am I right,
so,
sir?
Yeah. So
Yes,
for
okay.
testing the equality of the block effects, we use the upper F, and for testing the equality of treatment effects, we use the other F.
Second F
And
ratio,
we know the corresponding degrees of freedom, etc.
Yes, sir.
Okay.
Sir, I guess we can also introduce the concepts of random effects for each of the two sources of variation mentioned in the ANOVA table. That is, the first one is treatment effects, that is small v out of capital V, which is much more than small v, and the block effects, that is small b out of capital B, which is much more than small b.
So looks like you are contemplating a situation where the number of treatments available would be a larger pool,
Yes.
and what we are taking in our experiment is
It's
a
smaller
subset
one.
of that.
Yes, sir.
Or it could be in terms of the number of blocks.
Yes, sir.
That's what you are telling.
Absolutely,
Okay.
yes. And this would lead to random effects additive model with three variance components, that is sigma square treatment, sigma square block, and sigma square error.
So if you assume that both the situations prevail, there are a large number of treatments and a large number of blocks, you are making subset selection for both treatment and block,
Yes,
then
sir.
it is becoming a random effects additive model with both the treatment effect and the block effects in the model showing random effects.
Yes,
This is a
sir.
totally random model.
Yes, so we have three components, variance
Yes,
components.
very
here.
good.
Yes, sir. Now, on the other hand, we might have one of the two sources, that is fixed and random, thereby suggesting a mixed effects additive model that can keep both the fixed and random effects as well. That is mixed effect
Additive
model with two variance components. Am I right, sir?
Yes, you are very right. Estimation of variance components follows in a routine manner. The idea is to compute the sum of squares in the ANOVA table and their expectations under the true model that we envisage in terms of random effects model. So for the three sources of variation, we compute the sum of squares, we compute their expectation assuming the model is REAM, and then we use the method of moments to
Yes, sir.
estimate these variance components.
Yes, sir. This is very clear to me now. Now, I recall that we have also studied missing plot techniques with respect to randomized block design and Latin square design. Are you going to discuss that as well here?
Unfortunately, we don't have sufficient time to take up that matter.
Okay.
But don't you worry, you will learn much more than this thing in this course.
Okay, sir.
Let us quickly go over the LSD part, the Latin square design part. I repeat what you have mentioned before. You said a Latin square design is a row column design. It has two blocking factors designated as row and column. That it is a two-way elimination of heterogeneity design. That it is a three-way ANOVA model. In the sum of squares, we have row, column, treatment, and the error. That is why this is three-way ANOVA model. You said all that.
Yes, sir.
And why don't we start with the ANOVA table first?
Okay.
You have mostly depicted the scenario for RBD.
Yes, sir.
I'm just showing the extended version. This is all that you know already from your undergraduate study.
Yes, sir.
The sources of variation are rows and columns and treatments and the error.
Yes. Yes, sir.
Note that in a Latin square design, we are talking about as many row effects, as column effects, as treatment effects.
Yes,
So
sir.
it is called a Latin square design of order V if it involves V rows, V columns, and V treatments. That's why no wonder in the degrees of freedom, rows V minus 1, columns V minus 1, treatments V minus 1. But altogether we have V square observations. Therefore, total is V square minus 1, and the error DF is obtained by subtraction. That's what it gives you V minus 1 into V minus 2.
Yes,
And the computations of the sum of squares, they follow routine. And the sum of squares due to error, again you get by subtraction. And the F ratios that you see over there, they all refer to the sum of squares error in the denominator, because that is where you get an estimate of sigma square.
Yes, sir.
By pulling the sum, mean square error. Okay. That's why these three F ratios, they are geared towards testing hypothesis involving equality of row effects, or involving the equality of column effects, or involving the equality of the treatment effects. That's why you get these three.
Okay. So this is pretty much similar with that of the
Yes,
RBD.
yes. So can
only.
you explain the model and the computations above? What are the models and what are the computations?
Yeah, I will try it in my own way, sir. And here I am starting. In a Latin square design or LSD, there are two external blocking factors designated as row and column factors.
Very good.
And more than that, the number of options or categories for these two factors should be the same, and also it should be the same as the number of treatments to be comparatively studied.
Yes.
As an example, we may be interested in an experiment to study the growth of pigs of 6 different brands raised in 6 different pens and fed with 6 different types of food.
Okay, it's an interesting example. Yes, go ahead.
Now, these two factors, that is pen variation and food variation, may serve as the blocking factors designated by 6 rows and 6 columns.
Okay.
So, we need 6 into 6 is equal to 36 pigs to carry out the experiment. Each pig corresponds to one cell or each combination of a pen and a type of food.
Okay.
Now, for an LSD to be defined, each brand of pig has to be represented by the same number, that is 6 of pigs. In other words, there are 36 pigs in the study, 6 from each brand.
Okay.
Now, if the brands are denoted by the letters A to F, that is 6 letters starting from A, then we first develop an arrangement of these brands in the form of a 6 cross 6 square called a Latin square of order 6. And here is the arrangement.
So you are saying this is a Latin square of order 6.
Yes,
Would
sir.
you explain what is the meaning of Latin square? I think you mean to say that means all these letters, they come exactly once
One
in every
times.
row and exactly once in every column.
column,
That is
yes,
what is happening. Okay. So do you mean to say you are primarily interested in checking if the extent of growth is the same for all the 6 brands of pigs under consideration? And for that, different types of pens for raising the pigs and different types of food for feeding them are taken into account.
Yes, sir.
Maybe that's why these two types of variations have to be taken into account in order to examine the extent of growth. So your main target is extent of growth, but you cannot abandon the case that they are raised in different pens and they have got different food habits. That's why these two are the row and column effects, the blocking factors.
Yes, sir.
Also, if the number of brands of peaks is the same as the number of types of pen and is again the same as the number of food types, then you are in the framework of a Latin square design, as you said, and then you can adopt a Latin square, as you said above, a Latin square design of order 6.
Yes, sir.
Looks like this is all that you have in mind.
Yes, sir. All pairs of pen into food type will involve exactly one pig each, as we have shown in the diagram.
Yeah.
Likewise, all pairs of pig brands and food type will involve exactly one pig each, and the same is true for each combination of pen type and brand type.
So let's go back and try to see again. You are saying the rows represent the pens, the columns represent the food types. So there are 6 different pens, 6 different food types, and the animal, the 36 pigs, they are put here, and ABCD, etc. They represent the different treatments that you are trying to compare.
Yes,
okay.
sir.
So that is how you get a Latin square, where all cross types come exactly once. So we have got one row element, one column element exactly with one observation. So the letters come with the rows exactly with one observation.
Yes, sir.
Letters come up with the columns exactly with one observation. So the treatment, row and column, they all have cross section of one experimental unit. Okay.
Yes, sir.
What is a formal definition of Latin square then?
A Latin square arrangement of order V is a square of order V cross V, that is with V square cells, such that a set of V distinct symbols are placed inside the cells in a way that each symbol appears once each in each row and in each column of the square. That is the one which you have explained earlier.
Okay.
Now, when this happens, we say that we are dealing with an LSD or Latin square design of order V.
Okay.
There are altogether V square observations arising out of V square cells, and we stipulate fixed effect additive models involving all the observational random outputs as Yijk is equal to mu plus rho I plus gamma j plus tau k plus Eijk.
I can see that now you are incorporating in your model the general mean mu.
Yes, sir.
Now the second component looks like the row effect, third component looks like the column effect, and then fourth component looks like the treatment effect, and then the error.
Yes.
So you are primarily interested in tau, that is your treatment effect, but you have been wise enough to incorporate the other two blocking factors, the row effect and column effect.
But
Through
essentially,
this design,
the IJKs are all runs from 1 to V.
That is what you say.
Yes, sir.
From 1 to V, okay.
Now, we must note that for each combination of I and J, we have a specified K denoting the peak brand type associated with the ith pen and jth food type. Likewise, for each combination of IK, we have a specified J denoting the food type and so on.
Okay.
So, we are dealing with V square experimental observations.
Right.
So, we also know that the total sum of squares is equal to sum over Yijk minus Y bar minus so on and square of the whole thing.
Yeah.
And this has the decomposition like total sum of squares is equal to sum SSR, that is the row sum of squares, SSC, that is the column sum of squares, plus SS treatment, that is the treatment sum of squares, and the SSE, that is error sum of squares. So, here are the formula. SSR is equal to rho SS is equal to this.
You can skip this and then.
Yes, sir.
So, you have got the row, formula for row, formula for column.
Formula for treatment. And SSE is to be obtained by subtraction as we
From
have
the
done.
total.
Yes, sir. And here is the correction factor, which is G square by V square.
Okay.
Now, sir, we are told that this is also as orthogonal known as orthogonal splitting of total variation. Under relevant hypothesis of equality of parameter effects, we form the F ratio and carry out an appropriate F test with V minus 1
And
into
then
V minus 1 into V
2.
minus 2 degrees of freedom. Since we know that the error degrees of freedom is equal to V square minus 1 minus 3 into V minus 1, that is equal to the later degrees of freedom, that is V minus 1 into V minus 2. I hope I am able to explain so far. Am I, sir?
Yes, it is well understood at this level, but we will very soon see that there is much more to know and learn from practical point of view. Let me clarify.
Okay.
The triplet IJK is governed by any two of them, as you said, and as such we only have Bhaskar observations. Any two of them governs the third one. Third one is unique in view of given any two. And the three-way complete layout would have involved V cube observations for every combination of I, J, K. However, the Latin square design is an orthogonal design in the following sense.
So, can I explain these features? I think it is because the covariance between y bar I naught naught minus y bar I prime naught naught and y bar naught j naught minus y bar naught j prime naught is equal to 0.
Etc. etc. Let's try to
Yes, sir.
understand.
Yes.
So, what we are saying is that in this model, if I look at the difference of the treatment effects, it is estimated by the corresponding difference of the sample means. And difference of block effects, again row effects, again obtained by difference of the corresponding row effect means. Similarly for the columns. And if we look at the structure of correlation among them, we find that all pairwise differences, they are mutually
covariance is
orthogonal in
zero.
the sense of all covariance is 0.
Yes.
That is what is happening.
So, in the ANOVA tables, sum of squares due to rows, columns, treatments and errors all are mutually orthogonal, as you have just said. Moreover, in the model, we have additive effects, and so
We can talk about the model computation of error sum of squares,
Yes,
computation of the error degree of freedom, everything follows in a routine manner.
yes, sir.
Yeah, I only lament that our students know so well, but only this much. It is high time that they should have widened their understanding. We have so much yet to learn about all these things. We must unfold the fascinating world to them. They must appreciate the beauty of the world of design of experiments. We said all those things. These are all computational aspects that you are saying. So we have to understand much more than this in a much better way and giving deep insight into our understanding.
Okay, sir. So, we look forward to hearing from you.
Sorry, I am not very excited to give a routine exercise on data analysis underlying RBD and LSD. I hope you don't mind. You must have had classroom exercises and exam questions on these topics. At the end, I have included a few standard questions and some MCQs as your practice sessions.
Okay, sir.
We will now take up some exercises and at the end I will put some MCQs for you. So for the exercises I thought that I should dwell only with RBD and then for MCQ I can take up both RBD and LSD. As a matter of fact, in subsequent chapters we will find that there is much more general notion of design with one blocking factor and much more general notion of design with two blocking factors. These are unending scenarios to tackle real life issues. So much more is coming up in the next set of modules. So in this one we confine only to RBD and LSD in a limited way and try to have clear thinking on some of the issues that have been discussed in the text. Okay, let's take up question number 1. For an RBD with B blocks and V treatments, suppose one observation is missing. Argue that the design is still treatment connected as well as block connected. Recall, treatment connected means all treatment differences are estimable and block connected means all block differences are estimable, and we know this is trivially true in an RBD setup, but now you are saying that in an RBD setup one observation is missing. It could be anyone from any place. There are altogether B into V, so many observations, one is missing. That does not affect the model, but that affects the consideration for the estimation of the treatment effect differences or estimation of block effects differences. You have to argue that even though one observation is missing no matter where, you can still go ahead and estimate the treatment effects differences as well as the block effects differences. That refers to question number 1. Now question number 2, suppose in an RBD B less than V, we have more number of treatments than the blocks, but we are in the setup of an RBD. Argue that even if as many as B minus 1 observations are missing, the design is still connected with respect to both treatment as well as block contrast. It's a good problem. So you have got B less than V, and imagine any B minus 1 observations are missing. Then you have to argue that you can still estimate all treatment difference contrasts as well as all block difference contrasts. That is your question number 2. And question number 3 says, argue that in an RBD with B blocks and V treatments, there are B minus 1 times V minus 1 linearly independent observational contrasts, each with zero expectation under the stipulated model of an RBD, hence or otherwise justify that there are B minus 1 into V minus 1 error degrees of freedom. If you see the ANOVA table for RBD as was shown by Sagorika, that ANOVA table, it says error degree of freedom, so error as source of variation, degree of freedom B minus 1 times B minus 1. So you start wondering where is it coming from. It's not just from the splitting of the total degree of freedom and then taking into account the degree of freedom due to blocks or due to treatments. There should be definitely so many mutually orthogonal observational contrasts with zero expectation. So that is the problem here. You show that indeed in an RBD there are B minus 1 times V minus 1 linearly independent observational contrasts. Observational contrast means observations with coefficients plus minus 1 and 0, so that their expectation is 0. So each of these observational contrasts should have 0 expectation, they should be linearly independent, and then that will justify that you have got so many error degrees of freedom. So all the 3 examples, they depend on your understanding of the basic concepts of in the context of RBD, concept of estimation, unbiased estimation, and your concept of looking for observational contrasts with 0 expectation, proving their linear independence, and so on. These are interesting, thought-provoking, not very difficult, but basic questions that I would like you to take up and respond satisfactorily. Now I can ask Sagorika to read out the multiple choice questions.
So at first I am talking about the question which is related to RBD. So the first question is, in an RBD with B is equal to 6 and V is equal to 5, the computations were made available by the data analyst, which is for the 6 blocks, the sum of squares of yij's, that is sum over j yij,
the block totals,
and the squares of the yij's,
the raw sum of
squares are given. And so as the treatment totals and treatment sum of squares.
And also
the sum totals are given.
So all these are given.
So all these things are given, not the raw data. So the question is, a statistician wants to cross-check the computations, and how many cross-checks are necessary for this? And we have 3 options, 2, 3 and 4.
Let's try to understand the problem again. So there are B blocks, 6 blocks and 5 treatments, and these are the summary statistics given. The question is, if before proceeding ahead with the computation of ANOVA, sum of squares, mean square, F ratio, etc., it is better to have a cross check on this data because we don't have access to the raw data. So maybe we can check immediately and see if everything is right. So the question is, how many independent cross checks are needed to verify the computations, whether it is 2 or 3 or 4. Okay, what is the next question?
And next question is, it is also based on RBD. In an RBD with B is equal to 6 and V is equal to 5, 3 arbitrary observations are missing. Then the error degrees of freedom is given by which of the among four, that is 19, 18, 17, or it can't be computed. So this is also an option.
Okay, so 6 blocks and 5 treatments. That makes it 6 into 5, 30. The total is 30 minus 1, 29. And then due to blocks will be 6 minus 1, 5. And due to treatments will be 5 minus 1, 4. So 1 is 5, other is 4. 5 plus 4, 9. From 29 you take out 9, you get 20. Without any missing observation, error degree of freedom was 20. That much I can see. It's a simple computation in an RBD framework. Now they are saying there are 3 arbitrarily missing observations. You don't know what they are going out. Now you have to compute the error degree of freedom. So you have to justify how the errors are formulated now and how to compute the error degree of freedom. And with the question, there is also an option can't be computed
whether it is
because you don't know where those observations are lying.
Yes.
It may depend on their positions as well.
In that case, it would not be computed.
Yes, it's a good question. Okay.
Yes. And the third one is, obviously it is based on Latin square design. And the question is, in a Latin square design with 7 treatments, a total of 4 observations are found missing in an arbitrary manner. Then the error degrees of freedom is given by, again the first 3 options are 19, 26 and 23, and the last option is it can't be computed.
So when we say it is a Latin square design with 7 treatments, we also automatically mean there are 7 rows, 7 columns and 7 treatments.
Yes, sir.
And altogether there are 7 into sign or 49 observations. If there are 49 observations, total degree of freedom is 48. From that you take out row, due to row, 7 minus 1, 6. Due to column, again 6. Due to treatment, again 6. So 3 times 6, 18 is gone. 48 minus 18, 30. So in a normal case scenario, Latin square design, error sum of squares will have degree of freedom 30.
Yes.
Now the question is, 3 observations. Now how many?
Yeah.
4 observations are missing in an arbitrary manner. What will be the computation of the error degree of freedom? Good question again. Is that all, or you have something?
No,
Okay.
I have one
Okay.
more. The question is, in a Latin square design with 7 treatments
Right.
here, the ANOVA F test suggests that the row effects are not significantly different from one another.
Okay.
Now, accordingly, it is suggested that the data should be analyzed as an RBD with
Okay.
B is equal to 7, B and V both are equal to 7.
Okay.
In that case, the modified error degrees of freedom is computed as following these 4 of the options.
Yeah.
The first option is same as that in case of the LSD.
Right.
The second option is 36,
Okay.
then 43, and again the last option is it can't be computed.
So what does it say? You start with the Latin square design. You do your data analysis.
Yes,
You
with 7
compute the
treatments.
ANOVA F, and you find that the ANOVA F due to row effects that is insignificant.
Yeah.
That means you can. So you initially you thought the row effects are different from one another, but you get a feeling that the row effects are not significantly different from one another. So it is suggested that you take out the row effects and then only talk about column and treatment, so it becomes an RBD.
RBD.
That's the idea. Now what happens to the error degree of freedom now? Is it the same as that in LSD, or is it this number, that number, or it can't be computed? You need some more information, etc. God knows. Okay. To sum it up, what we did basically is, with our understanding about RBD and LSD in our undergraduate course, we went a little bit ahead. We kind of tried to brush up our understanding in terms of the various computations with reference to the ANOVA tables, and then we talked about some questions for a better understanding of some of the intricate issues involving the Latin square and the RBD. I was not very excited because these are all methodological issues. Not much theory is attached to these. But as I said, in the next set of modules, we are going to dig into the theory for block designs as well as for row column designs. There are many non-trivial issues. We only tested a little bit about the treatment connectedness and block connectedness with missing observations here and there. But we have a lot of things to understand. With this, I'll stop now. we look forward to module 6.